Have you seen this image?
Yes.
Well, this is the first image of a black hole. The first ever. And here there are the simulations, for example, for such a black hole with these parameters. So this one over here is the simulation. Of course, this would have been what we would have seen if the telescopes were perfect. They had the maximum resolution. But for the time being, we don't have such a high resolution. So what we see is a blurred image. If you blur this image, this is what we expect to see. And this is what we had actually seen. Now, this year has been the year of gravity. And I think these observations, both this one and the gravitational waves. Now, the gravitational waves were last year, right? Not this year. Anyway, these years. And these two observations will probably, I expect them to open up kind of a revolution in science. Well, probably not next year, but in the close future. Probably you will see that. Anyway, back to our old physics. If you remember, we had started discussing the magnetic field on Monday. We said that there are the magnets, which are a natural source of magnetic fields. They have a north and a south pole. And we said that we can show the magnetic fields, just like the electric field, we show the electric field in terms of lines. We can use magnetic field lines. And these magnetic field lines, they start from the North Pole and they go up to until the South Pole. And of course, these magnetic field lines, they in fact continue even in the magnet itself. So in a sense, these magnetic field lines, they don't really start anywhere and they don't really end anywhere. Okay, so let me ask you, what do you expect this integral to be? Yes, what should be the result? Two. You see, what did this integral represent? It was the Gauss law. In terms of the electric field lines, it essentially counted the field lines that crossed the closed surface. So if it was going out, it was counted as 1. If it is going in, it was counted at -1. And if there are charges inside, the electric field lines could enter the surface or leave the surface. They could have started inside, or they could have just start outside and terminate inside. So they gave us a positive count. This term is because the electric field lines start or terminate on the electric charges. So magnetic field lines, they don't start anywhere or they don't end anywhere. So this integral, well, I'm probably jumping a couple of chapters. This integral will be 0, always. Okay, that is, just keep in mind the analogy. Okay, let's forget it for the time being. So we have the magnets. Then we said that, okay, we also discovered that the currents, if you have a current, they also create a magnetic field, because when we put a current close to a compass, so if you have a compass, and if you put a current-carrying wire near the compass, so the compass will just rotate. Well, the compass is a magnet. It feels the magnetic field. So since the current changes the rotation of the compass, it just tells us that the current also creates a magnetic field. So it was kind of a connection between the electric field or the electric charges and magnetic fields. You see, before this discovery, we didn't know whether the magnetism and electricity, they were related or not in any way. So we had these rocks found in the east of Asia, east of Turkey, which had this property. So they had this additional force. At some point, we also knew about the electric field themselves, but we didn't know any relation between them. But now there's a relationship. This observation tells us that the current, which we know is described by moving charges, they can exert a force on magnets. But the magnetic field exerts a force on magnets. So basically, this shows us that the electric current creates a magnetic field. Now, we will discuss the magnetic field created by the current carrying wire, but if you want to find the direction of that magnetic field, again, your right-hand rule is your best friend. Whenever we are talking about magnetism, keep your right hand ready. So if you have your right hand, just point your thumb in the direction of the current in this case. So your fingers will point the direction of the magnetic field lines. So if this is the current carrying wire, the magnetic field lines is out of the screen at the top and into the screen at the bottom. Or if you would show it such that this is the current is out of the screen, so your thumb is in the direction of the current, your fingers rotate in the direction of the magnetic field line. These are the magnetic field lines. Then we said, okay, the current exerts a force on a magnet. What about the magnet exerting a force on the current? And they also exert, any current will feel a force in a magnetic field given by I times L cross B. If B is uniform. If B is uniform, then this will be the current. And then finally, we were looking at an example where there was a region of space which had a uniform magnetic field. And it was carrying a current, and this region was a circular arc with radius r. And in this problem, what we did was, okay, the arc is not straight. So what we did, we divided it into very small segments. This was dl. df was I cross dl cross b. And then we calculated df and then summed them all up to obtain the total magnetic field. Any questions up to here? Well, in this problem, in fact, since B is already uniform, there is an easy way. If you remember, we just had this df, we wrote down the components and summed them up to obtain the final result. But an easier way would be, let's say this is df, and the total force is the integral of df, sum of all these forces acting on each one of those segments, which is I dl cross b. Now, as we go from segment to segment, does I change? So take it out of the integral. Does B change? Take it out of the integral. So this is I dl cross B. Okay, I'm taking them out of the integral, keeping their order fixed. I'm not rotating these because the cross product changes sign. But the sum of all those dl's is just the total, this vector. Well, how do you sum vectors? Vector summation. Just you add one after the other one, geometrically. Well, here there is a vector. So the summation over the dl is sum over all these very small vectors. So we are basically doing a vectorial sum, and the result is just a vector pointing from this one to the end point over here. So this is f is I L cross B. What's the magnitude of f? So this is the total force is I L cross B, where L is this vector, B is into the screen. What is the magnitude of that cross product? Y0? Okay, first we have to discuss let's discuss the magnitude and then the direction. What is the magnitude? ILB. You see, the cross product, the magnitude is the product of the magnitudes multiplied by the sine of the angle between the two. L is in that direction, B is in that direction, and the angle between the two is 90 degrees. So sine of 90 is just 1. So the magnitude is ILB. The direction? In the y direction. That way. How do you calculate the direction of the cross product? Let me see your right hands. Fingers in the direction of L. Rotate your hand so that your palm points in the direction of B. Your thumb is the direction of the cross product. So the force is downwards. So this is the force acting on this system. Now, any questions? Sure, that's what we did on Monday. You see, on Monday what we did was, okay, if we have this such a very small segment, as your friend points out, on this segment there is a force. The direction of that force is, okay, this is the L. B is into the screen. So the force acting on this one is in this direction, perpendicular to this dl. And if I take this segment, the force is in that direction. If I take this segment, the force would be in that direction. And if you sum them all up, it should be pointing somewhat downwards. Without doing the explicit computation of Monday, you cannot really say that it is downward. But you can say this, that it is downward using this derivation also. I just compare with the derivation on Monday. This is easier. Any questions?
Böyle başlattık, bu tarafa doğru çevirdik
Well, you see, I'm not making any assumptions. It's what the derivation is actually telling me. You see, this is the force law we have. If you take a very small current carrying wire, that very small segment will feel a force, a very small force, whose magnitude is given like this, where this vector dl has a magnitude which is the length of the wire, that very small segment, and its direction is in the direction that the current is running. So that is our law, let's say. But in this particular case, in this special case, we know that B is constant, I is constant. So what I did was, in this special case only, I could take the I out, I could take the B out of the integral, because I doesn't change from segment to segment. The current is the same throughout the wire. B doesn't change throughout the wire. So I could just take them out. What remains, this integral, is just the sum of all these very small vectors, but that is this large vector at the end of the day. So I'm not starting with, oh, let me take this vector. No, I cannot do that. But in this special case, this law resulted in this relationship. But that is only for this special case. And because the things I used was I is constant, well, that will almost always be the case. And in this special case, B is constant. So I could just take them out of the integral. So let's see. What is the difference between a current carrying wire and a non-current carrying wire? Let's assume I have a copper wire. At some point, it doesn't carry any current. And at some other time, it carries a current. What changed in this wire? No, forget about the magnetic field. I just have this wire. I hold it in my hand. At some point, no current. At some other point, some current. What's the difference between these two wires? What potential? I'm not exerting any force anyway. So okay, I don't care about what I do outside. I'm just looking at this wire. If it doesn't have any resistance, then there's no potential difference. Okay, I'm looking for a very simple answer that I'm sure all of you know. Yes, there are moving charges. So that's what the current is, moving charges. But here it says that, now we have just stated over here that if they are moving charges, then there is a force. So which basically we can say that the force should be acting on the moving charges themselves, not the wire. Because the current is nothing but moving charges. So let's see if we can relate this force law, dF is equal to I times dl cross B. Let's try to relate this to the force acting on each one of those charges. Now let's start with what is the I? What was I? How did we define I? dq over dt. So if we put it over here, df is dq over dt times dl cross b, dq times dl over dt cross b. So essentially what I am doing over here is, this is my wire. I took a very small segment of this wire. Let's say that the charge density in this wire, no, let's forget about it. Let's say the total charge in this wire is dq. And on the average, they will be moving with a speed v. And so dt, the time it takes for all these charges to cross that point, will be just dl over v. or I, which is dq by dt, it is v times dq by dl. That is what I did. But then the force acting on this wire is dq times dl over dt is just v cross p. So the force acting on the wire is the total number of charges multiplied by the velocity of the charges vector product with the magnetic field. If we are looking for the force per unit charge, per single charge, F would be just whatever the charge of that single charge is, Q, V cross P. So if you have a single charge moving in the presence of a magnetic field, this will be the force that that single charge will feel, not necessarily on a wire. Now this is an example. Again, let's assume we have a region of space where there is a uniform magnetic field. And in this region, let's assume that we have a single charge, Q, moving with a velocity v at a given instant, moving with a velocity v. What will be its motion? Well, if we want to determine the motion, first we have to determine the force. Because once we determine the force, and let's say we know its mass, Newton tells us how to calculate its trajectory. So what's the direction of this force? This way. So V, let me see the hands. Your forefingers in the direction of V, the first vector. Rotate your hand so that your palm points in the direction of the magnetic field, and so this is the force. Okay, so as the charge is moving upwards, it has an acceleration towards the left. So its velocity vector will rotate. After some time, my charge will be somewhere over here. This will be the direction of the velocity vector now. What will be the direction of the force? Well, V cross P. Now it's also, the force is also rotated. So what is the angle between the velocity and the force? V dot F is always 0. You see, the force will always be perpendicular to the velocity. Always. Well, the force will be proportional to the acceleration. The acceleration will be always perpendicular to the velocity. Well, acceleration is the change in the velocity per unit time. So the velocity is changing, but these changes are never along the direction of velocity, which basically tells us that the velocity of this object will always be the same. So here we have a motion where the force is always perpendicular to the velocity and the speed of the object is constant. Not just any circular motion, it's uniform circular motion. What is the period of rotation? Well, let's calculate. What is the period? How do you define it? So you have this periodic motion. What's the definition of period? Yeah, the time it takes to complete one rotation. Well, we know its speed, it's v, and during this time t, it covers a distance 2 pi times r, whatever the radius is. 2 pi r over v, so this is the period. Well, most of the time we are interested in frequency, which is 1 over t, which is v over 2 pi r. Well, we know that it's doing circular motion. What is the central force? It's mv squared over r. Well, the force has to be equal to mv squared r, which is just F, which is the magnitude is QVB. Well, this tells me that mv over r is equal to QV, or v over r is equal to qv over m. Or the frequency of rotation is, well, v over, you see, here over there we have v over r over 2 pi, but v over r is just this number. It's qv over 2 pi m. Oh, sorry. This is QB. So you see, if you know the magnetic field, if you fix the magnetic field, if you know the mass of your particle, the rotation frequency is the same. Or independent of what the radius of the circular orbit is, it always takes the same amount of time to complete one full circle. If it is moving faster, then the radius of the circle is larger, so it takes the same amount of time. If it is moving slower, it takes a less amount of time to complete. It travels a less distance, the circumference is smaller. At the end of the day, it still takes the same amount of time. Now, this frequency is called the cyclotron frequency. The first particle accelerators, in fact, use this principle. No. Because the radius, you see, the idea is, the reason why it's independent is this relation over here. Its speed or its radius is proportional to its speed. If it is going twice faster, the circumference is twice as big, so it takes the same amount of time. If it goes if it reduces its speed by a factor of 2, its radius and hence circumference is reduced by a factor of 2. So it is always a fixed amount of time. Now, how did we use this to accelerate particles? Basically, we had such devices. So here we had an alternating circuit. So here we have the plates. We connect an alternating electric field, alternating potential, so we create an alternating electric field here. Inside, you put some ion. You know its mass. You put this system in a magnetic field. That's a uniform magnetic field. Close to the center, you put an ion source, which creates charged objects. It can be electrons, for example, or if you ionize the hydrogen atom, you can take the protons or electrons, whichever you like. But the idea is you know the mass. The mass, you input a charged object with a known mass. So it accelerates in some direction. Let's say it accelerates downward. Then it enters the region of magnetic field, so it will rotate. Now you have to adjust the frequency such that, you see, you put the charge over here, the electric field accelerated it downward, so it completes half a circle. When it reaches here, if you want this particle to keep on accelerating, you should better change the direction of the electric field. So when it reaches here, here we have an alternating circuit. So alternating potential source. So the potential changes its sign periodically. So when it reaches over here, the electric field should change its direction so that it was accelerated downward here. Now it is accelerating upward. Now it reaches the upper so-called D. Now it is moving faster. So it will go around a larger circle. Now when it reaches here, again you have to switch the direction of the electric field. So it should be pointing downward now and accelerating it. And then once more. And so you have your particle accelerated at every turn. Of course, the changes of the polarity of this potential is an alternating potential. The frequency of this alternating potential should match the time the charged particle takes to go from here to over there, which is determined by the B, the mass m, and the charge. So once you know the magnetic field you have, you know the charge of the particle that you want to accelerate, and the mass of that particle, so you know which frequency you should use for this source. And as long as your potential has the same frequency, you will get your particle accelerated, so it will go around larger and larger circles, and eventually you have some tubes over here which takes away the particle, and you have your particle. So this was called the cyclotron. So that's why that frequency is called the cyclotron frequency. Anyway, any questions on this derivation? So basically, the magnetic field exerts a force perpendicular to the velocity. It's always perpendicular to the velocity. So it cannot really change the speed of the object. It can change the velocity, but not the speed. Now, what about the work done by a magnetic field? How can we write down the work done by the magnetic field? What is the definition of work that any force does due to a very small displacement? F dot dl. The force multiplied by dl, the very small displacement through which the force is acting. Well, the force we know, qv cross b dot dl. But v is nothing but dl over dt. If there is no other force acting on my system, or even if there is a force acting on my system, the velocity of the object is nothing but a very small change, but that very small change is what we call the dl. If that change happens in a time dt, this is what we call the velocity of the object. But here we have the vector dl cross b. It is always perpendicular to dl. It is always perpendicular to b. So this is nothing but 0. So if you have two vectors, if they are perpendicular to each other, their scalar product is always 0, because the scalar product depends on cosine of the angle between the two. So what this tells us is that You see, magnetic field cannot do any work on an object. So if you remember the work and kinetic energy theorem, the work done on an object by all the forces acting on the object is just the change in its kinetic energy. Do you remember this? This was called the work energy theorem from 105. Now, magnetic field doesn't do any work, so it cannot change the kinetic energy of any charged object. Well, that is in fact what we had used above. We said that the magnetic field cannot change the speed. It only can change the velocity, the direction of the velocity, not the magnitude. So the kinetic energy is constant. So you cannot use magnetic field to stop objects, for example. Yes, because if you have many point charges, well, the magnetic field doesn't do any work on any one of them. And the total work it does would be just the sum of the works it does on individual objects. Other questions? Okay, so let me ask a question which I will not answer. Let's just assume we have these conducting rods connected to a battery. And on these rods, we have another conducting rod, but that is free to slide. So in which way the current will flow? Clockwise or counterclockwise? Well, this is the positive. The larger one is always the positive terminal. The smaller one is the negative terminal. So this is how the current will flow. What is the direction of the force acting on that rod? Let me see the right hands. Your forefingers in the direction of the current, your palm in the direction of the magnetic field. So the B is upward. The force is upward. In which way the rod will move? The rod will accelerate upward. Ignore gravity. I mean, just assume it's horizontal, for example. Well, of course, you can ask the question, what should be the current if this is vertical and you want the rod to be in equilibrium, to be at rest all the time? Yeah, you can come up many questions, but let's just, for this sample example, assume it's horizontal, there's no gravity, no other force. So this rod feels a force in the upward direction. It is displaced in the upward direction. What is the work done? Well, work done is F dot dl. F is upward, dl is upward, F dot dl will not be 0. But we said that magnetic field cannot do any work. What is doing work here? Anyway, as I said, this is a question I will ask and I will not answer. This is for you to think about. Something should be doing work over there. You said that it's not a magnetic field, so what? Anyway, now so we have the electric field, we have the magnetic field. In fact, we can have a system where we have both the electric and magnetic fields. We had seen that the magnetic field is Q times V cross B. And if there is also an electric field, well, the force due to the electric field is just Q times E. So if you have both electric and magnetic fields, this will be the force that any charged object will feel. This is called the Lorentz force. In fact, this is the kind of the most general force that determines how the charged object will move in the most complicated electric and magnetic fields. Have you heard of the Northern Lights? Yes, the others? Have you heard of the Northern Lights? Well, these are the Northern Lights. Did any one of you see them? Any lucky one? I also have that attitude. I haven't seen them yet. So do you know how they are formed? How?
Exits magnetic lines, and there are some particles comes from some. They are like bending because of the magnetic field. So
That's essentially the idea. So let's ask this question first. So here we had an example where we had the magnetic field in one direction and the velocity was perpendicular to it. It doesn't have to be always that case. Let's say you have a magnetic field in that direction. What happens if you send a particle not in that direction but in this direction? Let's assume that you have a region of space where you have a magnetic field. Eventually, we will say that this is the magnetic field of Earth. But for the time being, let's assume it's uniform. And let's just also assume that you send a particle with a velocity in this direction, not necessarily on the plane of the screen. So you have those magnetic field lines, and your velocity is pointing in this direction. So the force will be QV cross B. Let's also define the direction of B as our z-axis. Now B is in the z-axis, and the F is perpendicular to the z-axis because the cross product of two vectors is always perpendicular to both of them. So what is the z component of F? Zero. You see, B is in the z-axis, F is perpendicular to the z-axis, which means it doesn't have any z component. But this also means that the acceleration of the object in the z direction will be zero. The acceleration doesn't have any z component. So the velocity, the z component of velocity of the object is just constant. You see, one thing you have seen in mechanics is you can just separate x, y, and z components. Well, the magnetic field kind of mixes them. If the object is moving in the x direction, then it feels a force in the y direction. But no matter how it mixes, at least in this example, the z component of the acceleration is also always 0, so the z component of the velocity will always be 0. So in the z direction, it will just do a motion with constant velocity. Then we have the xy components. Well, there will be forces in the xy direction, and hence it will do a circular motion in the xy plane. So essentially the motion of this object will do a circular motion in the xy plane, but at the same time it will move forward in the z direction. So that's what we call a helix. So this object will basically move along such a trajectory. In a sense, it will be just circling these magnetic field lines and move in some direction. Any questions on this? It will have a helical trajectory. It's just like the spring. Now let's apply this to the magnetic field of Earth. So here you have the Earth. Let's say this is the magnetic north pole, this is the magnetic south pole. So it has all these magnetic field lines. And now we have the sun. The sun sends many charged particles to us. So this is where the sun is. So there will be, it's sending electrons and protons to us. So this is a charged object. So this object will enter the magnetic field of Earth. And once it reaches once the magnetic field becomes strong enough, it will start circling around the magnetic field lines. But the direction of the velocity of the object in the direction of the magnetic field line will be constant. It will not change. In this particular example, this is the velocity of the object. So if you just imagine the perpendicular direction and the horizontal direction, so you see, this velocity has a component in the direction of the magnetic field line, in the upward direction. So it will move in that direction. At the same time, it will circle the magnetic field line. So it will just go around such a helix. Now, of course, in this case, the magnetic field is not uniform. So there will be some forces acting on the charges. But at the end of the day, that charge will follow the magnetic field line, even if it's not uniform. And eventually, it will go to the North Pole. And just imagine here, the magnetic field line stretches a huge space. So there are all these charges coming towards Earth, and they are all concentrated on the magnetic North Pole. And when they reach the magnetic North Pole, they will enter the atmosphere, they will collide with the molecules in the atmosphere, and that is what is creating all those colors in the North Pole. So, and this is the origin of the northern lights. All these colors over here. And the colors are determined mainly by the atoms and molecules in the atmosphere. Now, is this example clear? You see, what we are doing over here is we have the three-dimensional motion. Okay, in mechanics you have seen, let's write it down. Let's write down the force. The force the velocity in general will have a x component, y component, and a z component. B, we have chosen the direction of B to be the z-axis, so it only has the k component. So let's open up that parenthesis, QB Vx. What is I cross k hat minus j? And j cross k hat I. And then you have k cross k, it is 0. You see, the force only depends on the x and the y components. This is why. The force depends only on the x and the y components of the velocity. So let's see, Vx. Yeah, okay. The force depends only on the x and the y components, as if there is no z component. And the force is on the xy plane in the ij determined by the I hat and j hat. So it's as if, I mean, if you have a Vz, nothing changes. We have this three-dimensional motion, but first we can split it into two. The motion in the xy plane and motion in the z plane, z-axis direction. Motion in the xy plane is independent of whether you have a motion in the z or not. But we have already seen that in the xy plane, if there is no z velocity, z component of velocity, it's just doing a circle in the xy plane. But then there is the z component of the velocity, but there is no force in the z direction. So the z component of the velocity is just constant. So this object is making a circular motion in the xy plane, but at the same time moving in the z direction. So it's doing this motion. And that is this helix. So it's doing the circle and at the same time moving in the perpendicular direction to the circle. And this application over here, well, here we don't have a uniform magnetic field, but the basic idea still remains the same. So if you have a charged object in a magnetic field, it always circles the magnetic field line. And its velocity in the direction of the magnetic field line doesn't change much. It changes a bit, especially towards when it reaches the North Pole, since the magnetic field is changing strongly over here, it will just go backwards. So after reaching there, the North Pole, the charged objects will just mirror back and go to the South Pole, and then it will just go back and forth between north and south. And in fact, this is how they are trying to build some fusion reactors. It acts like a mirror for charged objects, a magnetic mirror. Anyway, any other questions?
Why don't we have any solid lights?
I'm not so sure if we don't have them.
I don't mind.
These are the southern lights. Well, you see, there are not many people living there. There are many people living close to the North Pole. The Siberia, the Alaska, they can be seen there. But there is nothing on the South Pole. There is no continent. Okay, see you in 10 minutes.